Hello and welcome to this lecture. We're going to continue our study of linear transformation and introduce these three important ideas: range, null, rank, and something called nullity of a linear transformation. So these are very important subspaces associated with a linear transformation. So anytime you have a linear transformation, we'll associate some very important subspaces to it. Range and null are those two important subspaces. Rank is basically dimension of the range and nullity will be dimension of the null. It's very easy ideas, but very, very important, crucial. We'll introduce them in this lecture. Okay, so let's see what are the questions that one may ask about linear transformation, right? So typically when somebody gives you a linear transformation, if you really want to understand it well, you have to be able to answer a few questions about it, right? So that's the sort of thing we're asking here. What are the questions that people may be interested in? Okay, so here is linear transformation from R2 to R2. I'm showing the two R2s separate, right? Just for ease of illustration. Okay, so we've already seen that a subspace in R2 will go to a subspace in R2, right? So subspaces are preserved by linear transformation. This is a property we've seen already. Okay, so you may ask specific questions like, supposing I have a subspace in R2, which subspace in R2 is going to come to this subspace under this linear transformation T? Okay, so you may want to know the subspace to subspace mapping. Which subspace goes to which subspace? So this is a question that may be of interest, and you should be able to answer it. If you really understand the linear transformation well, you should be able to say, okay, I give you a line through the origin, which resulted in this line, which subspace in R2 resulted in this line. Is it another line? Is it the entire R2? Right? Those are the only two possibilities, right? What is it? So you should be able to answer that kind of question. Okay. The other kind of question you may ask is, supposing there is one point here. Okay, some point. This is not a subspace, right? So we know this point is not a subspace, but you may want to know all the points in R2 which under T will result in this red point, right? So you may want to know all the inputs that map to one particular output point by this T, or maybe this red may not have anything here that's coming in. That also is possible, right? So you may have no input reaching this, or even when there is some input reaching it, you may want to find the set of all points. Or maybe there's only one point here. I don't know. Okay. So these two questions are very reasonable questions to ask about linear transformation. And the answers to these two questions involve these subspaces called range and null. Okay. So let's begin. And then the matrix representation will be our major tool in helping answer this question precisely every time an actual linear transformation is given to you. Okay, so range of a linear transformation is an important idea that will help us formulate answers for these kind of questions. Okay, now this is a picture, right? So here I have the entire R2. The entire R2 under T will go to some subspace, right? So R2 itself is a subspace. So if you operate T on this entire R2, it's going to go to some subspace here, and that subspace is called range. Okay, so what is range? Range of a linear transformation is the set of all T of U for all U in R2. So you go to every vector here, you do the transformation, you will go to a subspace, no, eventually. That is called the range. Okay, this is actually range of any mapping or any function. Range is like that. You go through all possible inputs, the set of everything that you get will be your range. In this particular case, we know that range will be a subset. Okay, subspace. Range is a subspace. Clearly, so subspaces go to subspaces. R2 is a subspace. It's the entire space, but it's also a subspace. So when you transform with T, you will get a subspace. What about the basis for the range? Okay, so for instance, you may think that R2, maybe the range is the entire R2, right? Okay, or maybe the range is a line through the origin, or maybe the range is the origin itself. Who knows, right? So those are the only three possibilities, for range subspaces, right? So it could be entire R2, or a line through the origin, or the origin itself. Okay, so which one is it? You may want to know. So you may want to know the dimension of the range. Is it 0, 1, or 2? Okay, both these questions you may want to answer, and that again the matrix representation will help us. Okay, so how do we use the matrix representation to answer this question? It's quite reasonable. Think about what I'm saying here. Supposing you have T from R2 to R2 is a linear transformation, we're going to use the canonical basis, and T of E1 maybe goes to AB, and T of E2 maybe goes to CD. Now we know the matrix is going to be AB, CD, like this, right? So this is my matrix representing this linear transformation. Now the range of T, okay, right? So for the range of T, we know that a spanning set is T of E1 and T of E2. Okay, how do I know this? Okay, so remember, T of E1 is AB and T of E2 is CD. Any input U can be written as a linear combination of E1, E2. So any output of a linear transformation can be written as a linear combination of A, B, and C, right? So this is a easy enough thing to see. In case you want me to write it down, I can say that. So any U in R2 can be written as xe1 plus ye2. So any T of U can be written as xt of e1 plus yt of e2, which belongs to the span of T of e1, T of e2. Okay, so if you look at the range has to be the span of T of e1, T of e2. Okay, so I hope you see this logic behind this quick idea here. So spanning set is A, B, C, D. Okay, so yeah, I've put on a logic here. The same thing I wrote down, I've written it in the slide as well. So all vectors in range are linear combination of T. Now the range space of a matrix, okay, this is also, it can be the range, okay, range of the linear transformation, or the range space of the matrix, or the column space of the matrix. You see why it's called the column space, right? So now T of E1 is represented by this column AB, and T of E2 is represented by this column CD. So you can think of all the linear combinations of the columns as being the column space. Okay, it's the span of the columns of a matrix representing the linear transformation. Okay, so all these things are one and the same: range space, column space. Okay. So this column space, clearly range space, so column space represents the range of T. Okay, so if you find the dimension of the column space, you have found the dimension of the range of T. Same thing with the basis also. If you find a basis for the column space, you have found a basis for range T. Okay, so what is rank of a linear transformation? Okay, so let's work our way towards the basis and dimension and rank. That's where we're going to go. So let's say the matrix of a transformation T with respect to the canonical basis is A, B, C. Okay, we know range T is already, it's got a spanning set, which is T of E1, AB, and T of E2, C. Okay, now basis for range T, all you have to do, how do you go from spanning set to basis? Standard method is elimination, right? You start with the columns of the matrix and do elimination. Okay, so once you do elimination, a rank of T or M of T, rank of T or rank of M of T, the dimension of the range of T. So that's the definition of a rank of a matrix or rank of a linear transformation, dimension of range of T. Okay, so here is a few examples. All this is easy in theory, but let's see a few examples. So here are a bunch of linear transformations represented by matrices. You have to find out a basis for the range. Okay, the first one is a very trivial one, 0, 0, 0, 0. Okay, so in this case, you see that the range space, okay, the set of all linear combinations is nothing but the origin itself. Okay, so rank is going to be 0, right? So for the origin subspace, there is no basis, so it's a null set, so you have a rank of 0. Here's another example where you have 1, 0, 0, 1. So when you have 1, 0, 0, 1, clearly these two are linearly independent, so they themselves make a basis, right? 1, 0, 0, 1. You can do elimination if you like, but it's clearly linearly independent, right? So this is 1 here, this is 0 here. There's no way you can make a linear combination to make this 0. Okay, so they're not in the same direction. You can see it in many different ways. So this is rank 2. Okay, here's another example where 1, 3 and 2, 4. Okay, so here you may have to eliminate a little bit just to be sure. You may have to eliminate. Maybe the answer is clear to you. You know already what will happen if I eliminate. So you can put down 1, 3 and 2, 4. Okay, so this is row 1 and row 2. What do you do for row 1? Row 1 you keep as it is. And row 2 you replace with row 2 minus row 1 into 2. So you're going to get 1, 3 here. And then this is going to become 0. This is going to become minus 2. And at this point you can stop, right? So this is giving you a basis which is 1, 3, 0 minus 2. And you will get rank equals 2. So these two are linearly independent. So they are also a basis for the range of T. Okay, rank 2. So it's very easy, right? So it's just 2 by 2 matrix, just 2 columns, very easy to do this. And you can quickly find out from the spanning set, you can find out a basis for the range of T, which is basically after elimination, what you have left is the basis. And then how many basis vectors you have, that gives you the dimension. So here is another example, 1, 3, 2, 6. So here if you do elimination, notice what happens. 1, 3, 2, 6. I've cooked up this example so that you get something Very interesting. So you're going to keep 1 as it is because this is non-zero. So the first one can be as it is. R2 minus 2 into R1. I'm going to get, maybe I should write this a bit farther away. I'm going to get 0 here and 0 here. So you see the rank is 1 and the basis is just 1, 3. You don't need, you can drop the zeros from it. So this one has a rank 1. Okay. So I hope you see these kind of examples are very, very easy to do. In general, given an ABCD, you can do elimination and find out whether it's rank 0, rank 1, or rank 2. Rank 0, you don't need anything, right? You just stare at it and get the answer. Okay, so this is the definition of range of a linear transformation or column space of the corresponding matrix or rank of a linear transformation. Okay. All right. So let's look at full rank matrices. When do you say a matrix is full rank? Okay, a 2 by 2 matrix is said to be full rank if the rank is 2, right? So you have T of E1 is U1 and T of E2 is U2, and rank is 2 if and only if U1 and U2 are linearly independent. And if rank is 2, elimination will result in 2 non-zero columns. All these are very, very standard simple facts. U1 and U2 are in different directions, then they are linearly independent. Okay. Okay, so now that is range. That's all I want to say about range and rank. Let's now move on to the null of a linear transformation. Okay, so like I promised, these notion of range and null will help you understand questions about how the linear transformation is working. First, let's look at the null, and then we'll look at how this helps you understand the linear transformation better. Okay, so what is null? Null is basically the set of all inputs which map to the origin. Okay, so you have origin. Definitely origin is a possible output in a linear transformation because 0 goes to 0 in a linear transformation, right? 0 goes to 0 in a linear transformation, so null will always have the origin in it. Now there may be other elements in R2 which under T may get mapped to the origin. Okay, what does the null T do? It collects all those inputs in R2 which give you origin when transformed with T. Okay, so that is the idea. Okay, so this is the picture if you want to have it in mind. The origin, there might be a bunch of points. I'm missing out the origin here. The origin here will always come here. So these bunch of points which come to the origin is the null space. A very interesting property is null T is actually a subspace. Okay, so in this R2, from where null is coming, null T will be a subspace. As in, it might be the origin, or it might be a line through the origin, or it might be R2 itself. It cannot be any other set. It cannot be like how I've drawn it. This is all wrong. Okay, for a linear transformation, this cannot happen. For linear transformation, null T is a subspace. Okay, why? I mean, the proof is very, very simple. If you have U1 and U2 in null T, and you do a linear combination of U1 and U2, and then you take T. Okay, so what does U1 and U2 in null T mean? T of U1 is 0, T of U2 is 0. And if you take a linear combination of U1 and U2, and then apply T to it for any AB, what will happen? Because of the linearity, you're going to get A times T of U1 plus B times T of U2. Now T of U1 is 0, T of U2 is 0, so it becomes 0. So if you have two guys being in null T, their linear combination will also be in null T. So null T is a subspace. Okay, so very easy proof. And what is nullity of a linear transformation? It's basically dimension of the null of T. Okay, so just like you had range space, range and rank, you have null and nullity. Okay. So how to find a basis for the null space is an interesting question. So we could find the basis for the range space very easily, right? We looked at the matrix. The basis is the spanning set is the spanning set for the range is the columns. And you take the columns, you do a elimination, you get the basis for the range. Okay, very easy to get that. But what about null space? It seems a little tricky. It is a little bit different. So here is how you find a basis for the null space. Okay, so you have T, which is a linear transformation, as a matrix A, B, C, D, and the canonical basis. What is the null space for the matrix? Null space for the matrix, it's also called right null space because we do on the right. Set of all points xy such that the matrix ABCD times xy equals 0, 0. Okay, so when you have an xy as the input to the transform, the output coordinates are given by the matrix times the input, right? That's how the matrix represents the linear transform. So how do you find all the inputs which give you 0? When you do the transform, you find all xy which when multiplying this matrix give you 0, 0. Simple, isn't it? Very simple. But how do you find this guy? How do you find all these xy? You have to just solve a linear equation. It's a very simple linear equation, right? What is ABCD times xy? It is AX plus CY and then BX plus DY. If you have to make both of these 0, basically you have the system of what are called homogeneous linear equations, and the constant is 0, ax plus cy is 0, and bx plus dy is 0. Okay, so you can recall from math 1 that there is an elimination process, a very simple elimination process to solve this equation. Okay, so once you solve this equation, you find this entire null space for the matrix. Okay, so here is an example. So let's look at this example. So here you have the same examples as before. So 0, 0, 0, 0. You have to find the null space now, right? What is null space here, right? Set of all xy, which when multiplied by 0, 0 gives you 0, 0, is what? All xy, right? Any xy. There's no need to even solve any equation. There's no equation. You just get, for any xy, you get 0 equals 0. Okay. So all xy end up satisfying this. So the null space is the entire R2. Okay, so in this case, the null space is the entire R2, so nullity becomes 0, 2, right? Rank is 0, nullity is 2. Is that okay? For the 0, 0, 0, 0 matrix, it's very trivial. What about 1, 0, 0, 1? We saw already that rank was 2. Okay, so how do you solve this matrix, this linear equation? So when you have 1, 0, 0, 1, the equation you have to solve for the null space is 1, 0, 0, 1 times xy equals 0, 0. What is that equation? X plus 0 into y, that's 0. X equals 0, y equals 0. So when you solve this equation, you immediately get x equals 0, y equals 0. If x and y are non-zero, then no way these two are going to multiply and give you 0, 0. Okay, so the only solution for 1, 0, 0, 1 is just 0, 0. So the null space, so this matrix, null space equals origin. Just the origin, nothing else. Okay, nothing else will happen. Okay, so origin, what is the nullity? Rank, dimension of the origin is 0, so nullity becomes 0. Okay, so here is another example. Let's look at this one. 1, 2, 3, 4. Okay, you do this. 1, 2, 3, 4. xy equals 0, 0. Okay, so you write it down. You get x plus 2y equals 0. 3x plus 4y equals 0. So how do you eliminate here? Right? I'm going to take the second equation and subtract 3 times the first equation from it. So I'll get this x will go away. You do subtract, you get minus 2y equals 0, which implies y equals 0. So now you put that back here, you get x equals 0. So even though this equation look different, if you do the elimination, you're going to get 1, 2 and 0 minus 2, right? So you write it row wise now and do elimination. Now that's how you solve for the linear equation. I hope you remember from math 1 that you would write it row wise and do elimination here, and you'll get an eliminated form, and x plus 2y is 0 and minus 2y is 0, and that just gives you x equals 0, y equals 0. So for this also, the null space, right? So the null space, null equals origin. There's nothing else in this other than the null space. Okay, so here also nullity will become 0. Here is an example where you have 1, 2, 3, 6. Let's try that. Okay. So you have 1, 2, 3, 6. Multiplying xy equals 0, 0. So here is, you will get something that's mildly interesting. Okay, so if you write it down, you have x plus 2y equals 0. 3x plus 6y is 0. Try and solve for it, you're going to get 0 equals 0. Okay, so the only equation, if you eliminate, you do the same thing. This second equation minus 3 times the first equation, you're going to get 0 equals 0. So the only equation is this guy, right? So x plus 2y is the only equation. 2y equals 0. Okay, so so you know how to solve for such equation, right? So you make one of these as free variable, right? And then the other will become determinant. So maybe if you put any y equals u, x equals minus 2u works. Okay, so the generic solution is minus 2u comma u for all u in R. Okay, this is the solution, and this is also the null space. Okay, clearly this is a line through the origin. Okay, right, through the point minus 2 comma 1. Right, if you want to visualize it, you have minus 2 comma 1 point and this line through the origin. Okay, it's through the origin. Okay, this is minus 2 comma 1. So this is this guy. Okay, so this is the null space. and clearly the dimension is 1, so nullity becomes 1. So this is how you find null spaces for 2 by 2 matrices. It's very easy to do. It may either be 0, 0 or a line, okay, or the entire R2, which is a very trivial case. Okay, so here you get nullity is 1. Okay, so here's another example, a very trivial example. So now I'm going to do it in my head. Okay, we've done all these examples. So you see rank is 1 here, right? So see, if you look at the column space, it's going to be spanned by the first column and the second column. First column is 0, so you can just throw it out. It's going to be spanned only by the second column. So that is a dimension 1 space, which is a straight line through 1 comma minus 1. So what's going to be the null space here? If you look at null space, you're going to write down xy, giving you 0, 0. So you will get here that y equals 0. The second equation will also give you y equals 0. Okay. So if y is 0, anything with y is 0 is going to be in the null space. So any x comma 0, which means what? Anything in the x-axis is going to go to 0 under this. So the x-axis is a line through the origin and its dimension is 1. So nullity becomes 1. So it's easy given a 2 by 2 matrix to quickly compute rank and nullity. Okay, to compute the range space and the null space. Okay. So in general, for any linear transformation, just based on the above examples, and you can go through this more carefully if you like, if the T, which is a linear transformation, how do the range and null behave? If the range is the entire R2, then null is going to be the origin, right? The range is the entire R2. If the two columns are linearly independent, the only way you can linearly combine to get 0 is with 0, right? So nothing else can be done. So the entire R2, that's the range, then null becomes the origin. If range is a line, that is the only interesting case here. If range is a line in rank 1, then a null space will also be a line. Okay, so dimension 1, dimension 1. So you can show that. See, if rank is 1, then the two rows and the two columns are linearly dependent. So you can eliminate one row, it will go away, only one of the rows will remain. So you will naturally get a line through the origin. Okay, line becomes line. Okay. If the range is the origin, then it's the all zero matrix, then the null becomes the entire R2. Okay, so these are the only things that can happen in a 2 by 2 transform. So this means rank plus nullity is 2 in a 2 by 2 transformation. Okay, so a simple, full complete characterization of what is range, rank, null, and nullity. How is this going to help us with the problems we spoke about? It's more or less there, right? So you can look at the range space and from there know what subspace is getting mapped to what subspace. And then you can look at the null space and answer questions like what will get mapped to a point that we'll see in the next lecture. Thank you very much.